thought about it.
Thought about it.
You should have like played with the door for like a second, like make it like it look like you push it up and
Right.
okay, yes. Oh, it's like yes.
What are the lines?
Like these lines here.
Yeah.
So those are my side view electrodes. Stick of metal.
And then is the part in the middle like a tube?
Oh, you weren't doing it.
I thought you were doing it, and I was like, okay.
Yeah, the part in the middle is the salt bridge. In any electrochemical cell, as soon as, I don't know the other hand, but as soon as an electron flows out of one part of the cell and into the other, it creates a charge imbalance because that electron leaves, now you've got one less negative on that side. So the salt bridge contains cations and anions, and then anions will flow to the compartment where you're losing negative charge. So if the electrons flow this way, then in the salt bridge, the anions go to the left to balance the charge in the compartment. If the electrons are flowing in over here, and they're putting negative charge on this piece of metal, then you've got excess negative charge. The nickel, like in this case, the nickel would stick to here, nickel plating. You'd have fewer cations in this compartment, and then the cations in the salt bridge would flow right to balance the charge. It's just a way to make sure that the charges in each compartment stay balanced. So the same number of positives, same number of negatives. That's all the salt bridge is for.
Nice.
Okay?
Heard like a third of what you said.
Right.
I just can't hear it because I'm crunching. And also I'm like deaf or something because I can't hear
Okay.
people without such.
All right, so I'll try to get this is called a concentration cell. And the first thing is that if you remember from the equation that I had up here a minute ago, it's called the Nernst equation. And Nernst.
Like list.
Like this one. Let's try some.
That one.
Named after some guy, of course, but it's the Nernst equation. Okay? And it lets you figure out the cell potential for non-standard conditions. And in this case, it works for what's called a concentration cell. You can have cells like this one where you've got the same, like I've drawn here, the same metal for the electrode. They're not necessarily going to just trade electrons with each other. If you think like the example that I had up here demonstration-wise with the copper and the zinc the other day, where the copper metal came out of solution and stuck to the zinc, and then the zinc, okay, on Tuesday I showed you that. That's a spontaneous reaction. If you just take nickel electrodes and stick them in a nickel solution, that's at the same concentration, nothing happens. But when you change the concentrations, like in this case, 1 times 10 to the negative 3 molar and a 1 molar, that difference in concentration, think my Nernst equation over here. Once you change the concentrations and you change the value for Q, you change the cell potential. So by manipulating the concentrations of ions in the cells, in the compartments, you can create a concentration cell. Okay. That's the concept. So before I go to the final part of this one, are you good with these two equations, that the top one's going to be the oxidation, the bottom one's a reduction?
Would you give us the original equation, or would you just give us that picture and be like, figure it out?
We'll probably give you the equation.
Nice,
Yeah.
okay.
But the top one, I mean, you go from nickel to nickel 2 plus, that's an oxidation. The bottom one, you go from nickel 2 plus to nickel, that's a reduction. The cell potentials are the same. So if you solve this under standard conditions, the cell potential is 0. Because remember, at standard conditions, these would be the same concentration, whether it's 1 molar at 1 molar, or 1 times 10 to the negative 3, 1 times 10 to the negative 3.
But they're not.
But they're not. So that's where the Nernst equation comes in.
Do you solve later?
Okay? I want to go to the thing written in black. If you had to make an educated guess, what direction did the electrons flow? From the dilute to the concentrated, or from the concentrated to the dilute? How many people would say concentrated to the dilute? That would seem reasonable, right?
But it doesn't.
It's the opposite.
What?
But why?
Okay, so if you think about, okay, let's think about it this way. If the electrons flow from the right side to the left side, and you build up a charge on here, just in terms of relative amounts, is there a lot of nickel in this compartment that's dissolved? I mean, 1 times 10 to the negative 3, is that very concentrated or not very concentrated?
Not very.
Not very
So
concentrated.
you
So
want
there's,
more to.
comparatively, there's not a lot of nickel here that once you build up a negative charge, will come out of solution and stick. Okay, it's a whole nickel plating, metal plating that I was talking about the other day. If the electrons, though, flow from this side across, first question, what happens to the nickel metal in the electrode when this starts losing electrons?
More of it.
Nickel metal when it starts losing electrons. What happens to the electrode? Does it gain mass or lose mass?
Lose.
Loses mass. And as it loses mass, what happens to the concentration of nickel ions in this compartment? Does it go up or down? Up, okay. If you send those electrons to the right and you build up charge on the outside of this electrode, you've got a high concentration of nickel metal on the right side compartment, the concentrated compartment. So if I then take those extra electrons and I start pulling nickel out of solution, what happens to the concentration in this compartment? It goes down. Okay. So concentration cells work by taking electrons from the dilute compartment and then realize in this compartment you got the electrode and you got the solution, but it takes electrons from the nickel electrode here, runs across this way, builds up the charge. Nickel metal dissolves and increases the concentration. Nickel metal plates out and decreases the concentration. Okay. So in this case, the electrons flow from the left side to the right side, or you could say electrons flow from dilute to concentrated. Okay. So before I go to the solution to what's the value for the E, any questions about just this bit?
Not right now.
Okay. So that means, I'll put this in red, this is going to be dilute. This is going to be concentrated. Can you combine those into an equation? And I would hope you would say yes.
Yes.
Okay. So, I'm only going to be interested in, and I'm only going to write the ions because
That's all.
where's my Nernst equation? Look at the Nernst equation for Q. When you calculate Q, do you include solids in the Q calculation?
No.
No. So you're only interested in, for the concentration cell, the concentrations of the ions. And this is going to be, follow the, they will color code this, concentrated and dilute. And I'll write in the concentrations below, 1.00 molar, 0.00 to 10 to the negative 3 molar.
Wait, what?
Pardon?
How do I went from dilute to constant?
They do flow, the electrons do flow from dilute to concentrated. But remember all that Hess's law? The Hess's law from like way back when?
I'll just say yes.
Yes. Say yes.
I
You
do
say you can
remember.
combine equations. Okay, you cross out the things that
That are
are.
similar, the same.
But in this case, you have different concentrations of the ions.
Yeah.
So you can't just eliminate the ions.
Yeah, you cancel
okay?
that.
I'm ignoring the solids because when you calculate, I could write them in and I can say nickel solid and nickel solid.
But you don't use them.
But you don't need them because you're only interested in Q. Okay. So,
Okay.
oh my goodness.
Can you guys give us a problem like this?
I don't know, maybe.
Wait, we don't even have a next class, do we?
No.
We have a final.
Yeah. It's all right. Okay. What's the number of electrons that are moved?
2.
2, right? So n equals 2.
Why don't you add them? Is it because they're the same electrons? They're just moving about from one side to the other?
Yeah.
Okay. I'm just
Yeah, in
making
any,
sure.
in any cell, electrons move from, and remember, for the electrodes, you've got oxidation, you've got reduction, you've got the cathode, you've got the anode.
Yeah.
Okay, so electrons always move from the anode to the cathode. If you think about right here, what's the standard cell potential for this particular cell?
0.
0. Because at standard conditions, remember the concentrations are 1. If the concentrations are 1, then that number becomes 0. This term becomes 0, and your standard cell is going to be 0 volts minus. And then plug in the rest of this.
Oh, when it isn't. Okay. I got it. I get it now.
And you got the logarithm of, I'm ready to go, 1.00 to 10 to the negative 3 over. Somebody have speedy math fingers? What do you get?
Negative 3.
Not for the whole thing.
Not for the whole thing. Just for the log.
Right. What about for the whole thing?
Negative 0.0888.
So Rosalie, you said negative 3, right?
Or sorry.
I got
positive.
0.0888
Right.
for the whole thing.
So if you math, can you guys math that in your head?
No. Well, it's just since it's
So, are you good with this term being negative 3?
Yes.
What's 3 divided by 2?
3
1.5.
1.5, right? It's 1.5 times 0.6.
Wow.
What?
If
Okay.
we did pencil math, then why didn't you?
1.5 times 0.6.
1.5 times 0.06 is roughly 0.09. Roughly.
What? No. How? Like, how am I just supposed to know this? I do not have a brain. It's just like SpongeBob up there or something.
SpongeBob doesn't have a brain.
Exactly.
All right.
He just has another SpongeBob.
That would be your answer. So anyway, I asked that because like
I know.
having good number sets can be really useful. So like Rosalie, you answered that's a negative 3, and that's correct. So if you take, that's roughly 0.06 times 3 is roughly 0.18. Divide 0.18 by 2, you get about 0.9.
But don't we need at least 2 significants?
Right. I'm doing that to check your answer. I mean, if you're
Oh,
working.
okay. Just see if it's reasonable.
Right, and then when you're looking at like the ACS test or any kind of a multiple choice test, a lot of times you won't have the option of using calculators, and you'll get,
What? Do
seriously,
we
on
get
some
it?
tests you can't use calculators.
But
Do
on
we
the
get it?
ACS,
You will?
Yeah, you will.
Okay. Don't
And
scare
being
me.
able to manipulate a number like this is a pretty good skill to have. Okay, so that's the last thing that I have for you is a concentration cell. That's what it looks like. Electrons flow from a dilute to concentrated, even though you write it in this direction.
that sucks.
It is what it is. Okay. Any questions about that one? Because I got one more short topic that's mostly about notations. Then we'll go do lab.
Oh, yeah, very significant. Oh, I'm so glad we're Tuesday. That's so nice. Yes. I have like 5 more copies left for chapter 15. I slept in chapter 16. I have to do chapter 17. I'm just like,
Okay.
maybe I'm just.
There is a notation for electrochemical cells that you need to be aware of because it may or may not show up next week. And it works like this. There's a double line.
Has nothing to do with those rabbits.
And that represents the salt bridge. Okay. When you write this particular notation, I'm going to put this in red. You've got an anode reaction and a cathode reaction. You need to be conservative. And remember, the anode's going to do the oxidation, the cathode's reduction. If I look at the zinc, reduction or oxidation? Oxidation. Okay. So I'm going to write this as the zinc electrode. I'm going to put a single line, and I'm going to put the ion that's in the compartment, which is zinc 2 plus. So you have electrode, cation in the compartment. And then on the other side, you're going to write this as the cation in the compartment, electrode. That's the notation that you may see this.
So what would be like an example of how, like when it's, like what would it be
Do you have that one, Angela? I don't remember that. I don't remember exactly what the question was, but it had, it was like, easier if I just. Okay, so this was a question on the test that Angela had, and the question is, what's the cell potential for the cell that's indicated here? With the following potentials. And that's a negative, right? I guess that, yeah. It's negative. Okay.
So one.
Okay. So then, it's asking you to remember that you've got oxidation on this side, you've got reduction on this side. So this would represent your compartment, or your cell diagram. So you have a cell looks like this, salt bridge, electrode.
Right.
The nickel is here, the silver is on the right. Electrons are going to flow like that. Okay. That's what this notation is. So if you're solving this, remember it's E reduction cathode minus E. Spontaneous or non-spontaneous?
Spontaneous.
Okay. Anyway, that's what this notation indicates.
Okay.
Salt bridge, oxidation compartment, reduction compartment. Electrodes. Just to give you an idea of a slightly different and I'll make a focus point here. For this one, same oxidation. In this compartment, you got a reduction where iron 3 plus is going to iron 2 plus. This is your reduction. And you have a platinum electrode. So in other words, in this particular cell, there's no solid iron present. The transfer happens at the surface of the platinum. There's no buildup of iron on the surface of the platinum because all that's happening is the iron 3 is gaining 1 electron and turning into iron 2 in solution. But that reaction, like if here's the surface of the platinum, you got iron 3 here for a minute, it gains 1 electron, turns into iron 2, and then it leaves. So iron sticks, reacts, and leaves. There's no buildup of iron on the surface. This particular cell notation has an aqueous reaction happening for everything at a solid electrode. Okay. Slightly different notation, still anode, oxidation, reduction, cathode. Just a couple things happening in solution.
And would, so then in that case, would the cell potential, does that have its own equation just for the iron?
Yeah, you have you look at it as copper. So on the chart, you would be able to find, or you'd be given the reduction potential for that one and the reduction potential for that one. Because you're not interested in this stuff. This is your oxidation, right? And the oxidation, even though the potential, they're always written in a reduction potential fashion. So even though in this compartment and at that anode, oxidation occurs, you still write it as a reduction equation. And when you go to look in like my book or wherever, you'll get this, and it's going to be a positive or negative number, whatever happens to be. I think this one's a negative. I think it's 5.4 volts. I don't know this one. But this one, you'd still write it as a reduction potential, meaning it's gaining the electron, and then you'd have whatever that value is. And if you were asked for the cell potential, you're still doing reduction potential at the cathode minus reduction potential. Sorry.
So if we were to, so if they were to ask us about like the other stuff that we just learned, the delta G stuff and all that stuff, would we have to double the iron? Because that one's
You
only.
would, yeah, you'd need to double it to balance
make
the charge, but
electrons.
remember that these numbers are intensive, so. you
Right,
don't-
so that doesn't matter for that equation,
Right.
but for a different one it might.
Yeah, like this one right here, that Angela asked about this one the other day. The tendency for people is, because you wanna balance the charges, which you do need to do.
Right.
The tendency is to wanna double everything here and then double this.
Right.
And that's why Tuesday I kinda stressed that this is intensive and it's based simply on the transfer of electrons. It doesn't matter how many silvers you have or how many electrons you transfer. That value is the same.
Okay.
Alright, that's all I got. Questions?
So Tuesday's just gonna be big.
Tuesday's just review, come with questions, I'll probably have at least a smattering of things from all year, but take some, I would take some time over the weekend. You've all got the text, I go through the text, look at the summary at the back of it, and just scan it for things that you don't remember. And if you don't remember, write down some questions and bring them in. Amber, are you running assignments Tuesday as well? Okay. I don't have this room, I don't think, until 6 something, so if Amber's running SI earlier, wherever you got it, then we'll just plan starting about 6:15. But it's just review, no new material, that's it.